start recording. And I'll pull up my screen here. Right. Well, good morning, everyone. I hope this is going to work out pretty well. How are you both holding up so far? How are things?
Okay.
Okay. All right. Well, today I really want to get into what's called Hilbert's Nullstellensatz, and this is a way in which we're going to try to relate prime ideals with certain subsets, and then we'll try to use this to define what we mean by an affine variety. Right, so I'm not really sure how much material I get through today, but we'll see how far we get. So just to start off with a few quick announcements, remember that Friday's lecture is on YouTube now, so you can see the link here. I'll have office hours at the usual time, usual place, 11 to 12, and then 4 to 5. And the next homework assignment is going to be due next Friday. So I was a little bit slow in getting it posted because I wanted to move around a couple of things. But homework number 7 is posted online now. So if you do have any questions about that assignment, please let me know.
I have a question. Is it next Friday or this Friday?
Oh, sorry, I meant to say this Friday.
Okay.
Yeah, so this coming Friday, the 17th. And certainly if you need more time to get these things done, that'll be fine. I'm actually debating about pushing back this homework assignment until the end of next week. So giving you 2 weeks to work on it, depending upon how busy everybody is. Okay, so let's do a quick recap of some of the ideas. So first, let's start with an algebraically closed field, and we're going to denote R as the polynomial ring and n variables over this field. So remember that this ring is an integral domain, and we actually know a lot about the maximal ideals sitting inside of this integral domain. They're always going to be generated by n polynomials in this form here, right? x1 minus a1, x2 minus a2, so on and so forth. So I'm going to come back and use this a little bit later on today, that I know what every maximal ideal inside of this integral domain looks like. Next, we talked about this idea of an affine variety as coming from this quotient ring. So now, let's say that F is a field. I am not assuming F is algebraically closed. So later on, I'll kind of show how we're going to bounce back and forth to when either F is algebraically closed or F is not. So for the moment, assume that it is not. Then remember that this ideal generated by a certain set of polynomials is a prime ideal if and only if this here is an integral domain. So for the moment, I'm going to assume that this ideal I is prime so that this quotient ring here is an integral domain. And once we do that, then we'll define this set here, this Vi of F, to be an affine variety. So here what we're doing is we're asking what are the set of points that vanishes at every polynomial in this ideal. So another way to say that is that if I have these M generators, that I want to know what are the simultaneous set of zeros for these M polynomials, right? So it's like here I have M equations, N unknowns, and I just try to set things equal to 0. So that's what I mean by this V sub I of F. And in general, this is what we're going to call an affine variety. So I'm going to come back and say a bit more about this today as we try to generalize it in a couple of different directions. So more generally, say that we have this prime ideal, right, just like before. And of course, we're going to assume that our O here is an integral domain. Then remember that every element from this integral domain really can be viewed as a function, where here I'm just going to take a point P and I will evaluate that function at this point P. So we proved before that this is nice, it's well defined, but again, elements from this integral domain O can be viewed as functions here for this affine variety. So we're going to try our best to play off of this more and more today. So again, let's say that we have an affine variety. We can talk about the Zariski topology on this set by doing the following. We'll say that a subset is closed if there is another subset T of R where we can think of this subset as the zero set of this set T. Right, so this is going to be very close to what I just had on the previous slide. But again, this is what it means to be closed. It looks like the zero locus here for some subset T. Similarly, we'll say that a subset is open if it is the complement of a closed set. So again, we have this idea of closed sets that look like that they're the zero locus of some subset T, and then an open set just means that it's the complement of a closed set. So putting all of this together, we actually realize that we have a topological space as follows. So we proved before that if we take a look at arbitrary unions of open sets, those are open. Finite intersections of open sets is also open. So I can now put all of these together and say that if I look at the collection of all open sets, then this forms a topology. And so I put this together with X to say that I have a topological space. So all of this is typically called the Zariski topology, named after Oscar Zariski. All right, so again, we're going to try to take all of the open sets and put them all together. That just corresponds to every possible subset of this ring R. Right, every possible subset will then give me back all open sets. So in the homework assignment that will be due this coming Friday, I do have an example for you to work out when X here is just the affine line. So there I do want us to focus on what do the possible open sets look like if X here is just A1. So let's go back to where we were before. We'll say that F is a field. We'll let R be the polynomial ring in n variables. And for today, let's let X be the whole affine space. So not just the subset, let's let X be the whole thing. And we'll try to write down a few definitions here. We'll define, just like before, Z of T to be the set of points where things vanish in T, where everything in T vanishes. Right, so again, Z of T will be the set, what we're calling a closed set. And let's let I sub V be the set of polynomials that vanishes along a subset X. So here V. Let's take a subset V, and let's ask for all of the polynomials that vanish along this subset. Right, so Z and I are kind of fundamentally different. Z is a subset of affine space, but I is a subset of the ring. And what I want to do is play these two off of each other. Right, one will be a subset of the affine space, the other one will be a subset of the ring. So our big theorem for today actually fits into 6 parts, and so I'll try to read them out here as follows. Number 1, Z of T is a Zariski closed subset, while I of V is an ideal. So remember that Zariski closed, this is just the definition of being Zariski closed, that Z of T for some T, it's just our definition of being a Zariski closed subset. I of V here says something about subsets of the ring R. So this is a very nice subset of the ring R. It is an ideal of the ring R. Next, let's say that maybe I have 2 subsets, T and S. And let's say that maybe S is slightly larger than T. Then I have a reverse inclusion here on Zariski closed sets. So if T is smaller than S, then Z of T is larger than Z of S. All right, so here again I have like a reverse inclusion. Similarly, let's say that I have 2 subsets of X. So let's say that W is larger than V. Then it says that I of W is smaller than I of V. Right, so remember here, in this statement, everything is an ideal. So now we're saying that the ideal I of W is smaller than the ideal I of V. Right. Next, say that we have now any two subsets, V1 and V2. Then the ideal here for this union is the same as the ideal for this intersection. Right? So this allows me to kind of interchange unions and intersections in this way. Right? Now we have a couple of ways to see how T and V are related. So first, let's say that T is this subset. Right, so let's say maybe that T is the subset corresponding to an ideal. Then this says that V is contained in the zeros of T. Right, so again, this kind of shows this weird kind of duality. So if T looks like IV, then V is contained in Z of T. Right. And now here's the big one. So I want to take some time to kind of walk you through this. Finally, let's say that my subset V is the zero set of a subset T. Then I have two statements. So one is that I can actually replace T with the ideal generated by T. Right, so again, if I know that V is the zero set of a subset T, then I can really replace T with the ideal generated by T. So the reality is I might as well think of T not just as a subset of this ring R, but I should really think of T as an ideal of the ring R. Right, so this is one of the important statements. I can always replace T with an ideal. Number two, I have the following inclusion, that with this ideal I, being the ideal generated by T, excuse me, then the radical of this ideal is contained in the ideal of V. So I'll say during the proof a little bit later, what do I mean by the radical of an ideal? All you really have to know is that the radical of an ideal is itself an ideal. So this actually now says that I have containment, that the radical is contained in IV. Finally, I have a stronger statement. Whenever F is algebraically closed, then actually I have equality. So that is IV is equal to the radical of the ideal generated by T. Right, so again, this equality here holds whenever F is algebraically closed. Right. So of course, I do want to go through the proofs of these 6 statements so you can kind of see how everything works. So let me just make a couple of comments here. This very last part of the statement, that IV is contained in the radical of I, whenever F is algebraically closed, that statement there is typically what's called the Nullstellensatz. So there was a German mathematician named David Hilbert who really was very interested in playing around with polynomials and rings and so on and so forth. And so one of the fundamental theorems that he proved was about how the zeros of a collection, the set of zeros of a collection of polynomials are related to different rings. So of course, because David Hilbert was German, you have this theorem here, the Nullstellensatz, which literally means the zeros statement, so the zeros theorem. So again, the zeros theorem really says that this allows me to figure out how the ideal generated by the zeros of a set T are related to the radical of the ideal generated by T. Right, so I do want to try to say a little bit more about this later. The homework set this week, homework set number 7, does give you an example of all of this here, so that way you can see what does the radical mean and really how is the radical related to this ideal IV. But for today, I'm not really going to go over any examples. I do want to try to go over the proofs of all of this. Finally, I wanted to say that we have a definition here. We say that a subset V is Zariski closed, you'll remember, if V looks like Z of T for some subset T. I want to make a slightly more general theorem, or I should say definition here. Given any subset V, so any subset V of X, I'll define the Zariski closure as the following. So here you'll take the ideal of V, and then you'll take the zeros of that. So again, take the ideal of V, that we know is going to be a subset of R. So then take the zeros of that. This now is a closed set. So I want to bring your attention here to statement 5. And this says here that if I let T be I of V, then V is always contained in Z of I of V. So the Zariski closure really literally is the smallest Zariski closed set that contains V. Right. Again, in the homework assignment this week, I will have you work out an example of how all of this works. But again, the Zariski closure, you can think of that as the smallest Zariski closed set that contains V. Right, so this will be the definition that we'll use for Zariski closure. Okay, so any questions before we start to go over the proofs of some of these statements?
Yeah, so how do you show this is the smallest?
So the quickest way to say that is that you have to kind of use a couple of the lemmas up here. I should say a couple of the other propositions. So for example, you might want to use, say, something like this number 3 here. So number 1, hopefully you believe that V bar is closed because it is Z of some set. So V bar itself is closed. If there were another set that were closed containing V, let's maybe call it W, then W looks like Z of I for some I. And then if you just kind of play around with property number 3, then you would see something to the effect of I would have to contain IV. You just kind of just work through there. I'll also say that there is a very nice short proof that's in Hartshorne's Algebraic Geometry. It was within like the first 3 pages of the book. So the proof really isn't hard. It's something I don't really want to say here in class, but it's really not too hard to work out. You just assume that there's another Zariski closed set. You relate that by saying it's Z of I for some other ideal, and then you have to ask yourself, how is that ideal compared to I of V? Right, but it's not bad at all. Okay, any other questions? All right. Okay, so let's try to do the proofs of these statements here. So let's start off by showing the first one. So of course we know that Z of T is a Zariski closed subset. That's just by definition. So I need to show that I of V is an ideal. To show that something is an ideal, I have to show 3 statements. First, that 0 is in the set. Second, that it's closed under differences. And third, that it's closed under products. Right? That's just what it means to be an ideal. I have to prove those 3. So to show that 0 is here, let's denote 0 as the 0 polynomial. Right? So it's just a constant polynomial, which means if I evaluate this polynomial at P, I just get back the number 0. That's just what the 0 polynomial means. But if it's 0 for all P in V, then by definition, the 0 polynomial is in this ideal. Sorry, it's in this set. So you notice all that I'm doing is I'm just evaluating at everything that's in the set V. I just want to make sure that I always get back 0. So what about the second statement? Well, let's pick F and G in our set I. Then I know that if I evaluate at P, then I always get back 0. Right? That's just what it means to be an I of V. If I evaluate at any point P, then I get back 0. So now let's take a look at the difference of the 2 polynomials. Right, so now I can evaluate the difference at P, and I just get 0 minus 0, which is 0. So that means that the difference, F minus G, has to be in this set. Right? Again, all that we're doing is just evaluating at P. So finally, what if we take products? So here now, I'm going to take lowercase r and capital R, and let's take lowercase f in our set IV. And just like before, we're just going to evaluate. Right? So if I evaluate here, then I just get RP times 0, which is 0. So that means that if I evaluated P, I always get back 0. But of course, if I always get back 0, once again, that's just what it means to be in the set IV. Right, so we do know that IV itself is an ideal. Okay. All right, so let's move on to the second statement now. So here, we want to say something about how one set is contained in the other. So let's say that T is contained in S. And I want to show that Z of S is contained in Z of T. So to start with the point P in Z of S, what that means is if I take any polynomial f in S, then it has to evaluate to 0. Right, that's just the definition of Z of S, the zeros of S. But of course, T is contained in S, so then that means that I know that f of P is 0 for all f in T. Right? If it's true for the larger set, it's definitely true for the smaller set. If it's true for everything in S, it's definitely true for everything in T. But of course, now that just means that the point P has to be in the 0 set of T. Right? Statement 3 is almost exactly the same proof. Right? So let's say here that you pick a polynomial in I of W, then that means that it has to vanish for everything in W, but V is contained in W, so that means that it has to vanish for everything in P, right? If it's true for the larger set, it's definitely true for the smaller set. So then this means that F here has to be an IV. Right? It's almost exactly the same proof. Okay. All right, any questions up to this point? Okay, all right, so we're about halfway done. All right, now let's show 4. So now I want to show this thing about what happens, how the union is compared to the intersection. So first, let's prove that I of the union is contained in I of the intersection. Right, so I'm going to pick a function that vanishes on all of V1 and V2. So what that means is F is 0 for all P in V1 union V2. Right, that's what it means to be an I of the union. So it vanishes in all of V1 and V2. But now if you stare at this, this means that F is 0 for all P in V1 and F is 0 for all P in V2. Right, again, if it's 0 for all points in the union, then it's definitely 0 for all the points in the first and it's 0 for all the points in the second. But I'm using this conjunction here, and. Right, this conjunction here, and, is just the same thing as saying the intersection. Right, whenever I have a conjunction here, and, it just means the intersection. So that gives me one containment. I of the union is contained in I of the intersections. Right. Now let's do the other direction, and it's almost exactly the same proof. It's really nothing different. Now I want to show that I's for the intersection are contained in I's of the union. So let's pick a function that's in the intersection. Of course, what that means now is that it has to be 0 for everything in V1, and it's 0 for everything in V2. Right, so I'm using that conjunction and again for the intersection. But if I stare at that, that means that f of P has to be 0 for all P in V1 or P in V2. But of course, for it to be 0 for everything in the union just means that F is in I of the union. Right. So again, it's almost exactly the same proof. We're just kind of just looking at the words, reversing things around. Okay. All right, so now let's do statement 5. So what I'm asking here is, how is I of V related to Z of T? So here I want to prove that if t is equal to I of v, then v is contained in z of t. Right, so again, if t here is equal to I of v, I want to prove that v is contained in z of t. Right, so let's try to back up to say, what are we trying to do here? So let's start with the point P and V. So then what this actually means is that for any f in IV, then we have to have f of P is 0. Right, so again, if I take any f that's in T, T equals IV. Because T equals IV, IV is by definition the set of polynomials that vanishes for every point of V. So for any f in T, f of P has to be 0. But because f of P is 0 for all f in T, that by definition just means that P is in Z of T. So this here is just a matter of semantics to kind of get everything to work. Okay, so we've actually taken care of all the easy parts. The last one, statement 6, is actually the hard part. Right. So to this end, I need to make a couple of definitions so you can see what we're doing here. First, remember that the ideal generated by T, I can really write in the following way. So here what we're going to do is take finite sums where g of k is in R and the f of k is in T. T could be an infinite set. I don't care. T could be infinite. All that I want to say here is that take a look at these sums where I'll pick the first one, f from R, and I pick the second one, f from T. Right, so this here is actually an ideal. So first I want to show that the 0 set is the same as the 0 set for the ideal generated by I. So let's do containments in two different directions. Pick a point P in the 0 set of T. Then for any f in I know that I can write f as a linear combination in this way here. Right, so it looks like some gk's, fk's, but now if I evaluate everything at P, remember that the fk's here are all 0. So I'm just going to evaluate at P and I get back 0, which means that my P is actually in the 0 set here for I. Right, so again, if it vanishes for at T, then it has to vanish here for any function in I. So this gives me containment in one direction. Okay, so hopefully that's not too bad. Now let's go in the other direction. Well, we know that T is contained in I. So by part 2, Zi is contained in Z of T. Remember how we said that if T is contained in S, then Z of S is contained in Z of T. So here we're just reverting back to what we've already done. Right, so that means now we definitely have equality here. Okay, so that was the first half. Right, now let's do the next half. So I'm going to prove that IV here is actually equal to the radical of I. So first I need to define for you what the radical is. So the radical is defined as the set of elements in R where some power of this polynomial is in I. All right, so again, it's a set of elements in R where some power has to be in I. Right, hopefully you'll see how the proof goes where we use that. So now pick an element here from the radical. So of course what this means is that some power I can write here as this linear combination. Right, because some power has to be in I, so I can do this. So now let's just evaluate at P. So based on what I just said before, if I evaluate this power at P, I should get back 0. But we're working inside of an integral domain. So if the power here is 0, then that means that the function itself evaluated at P has to be 0. Right? So of course, this means that f itself vanishes everywhere. So we have here containment in one direction. Right? So one direction here really is not too bad. Unfortunately, the second direction we are not going to be able to do here in this course because this is a major result by David Hilbert. This, of course, is the Nullstellensatz. So this says that we have containment in the other direction whenever f is algebraically closed. And unfortunately, we just cannot do this here in this course. So I may be happy to talk about it at some point later, but at least for right now, we just really won't have the time to go over the proof of this here. Okay. Okay, so any questions on how we did these 6 statements? Right. Okay, well, let's talk about maybe some applications and some definitions we can pull out of all of this. So let's go back to our case where f is the field. Remember that we don't need to assume that f is algebraically closed, just that f is the field. And let's let X be any Zariski closed subset, right? Any Zariski closed subset that you want. So the following two are equivalent. It says that I cannot write V as the union of two proper Zariski closed subsets, right? Proper just means that each one of these here is not V. And Zariski closed just means that it looks like the zero set of some collection of polynomials. That is equivalent to saying IV is a prime ideal. Right. So again, we're saying that we cannot write V as a union of two different Zariski closed subsets if and only if IV is a prime ideal. So this is kind of a weird thing because notice that on the one hand, here we're saying something about these closed subsets being like the union of two other closed subsets, but I'm replacing that with a really simple idea, which is that this thing here is a prime ideal, right? And of course, we're going to know a lot about prime ideals a little bit later. So let's use this to write down a couple of definitions. Any non-empty Zariski closed subset satisfying either of these two is said to be an affine variety. So you can use either one of these definitions as an affine variety. In fact, notice that this IV is a prime ideal if and only if this quotient here is an integral domain. But remember that this is actually how we define affine varieties at the very beginning, is that we really want the quotient here to be an integral domain. So now we have a slightly more general definition. Now what we're going to say is pick any Zariski closed subset here that you want. Then, as long as this quotient here is an integral domain, then we'll call this an affine variety. And this corresponds exactly to when this here is a prime ideal, and that corresponds exactly to when we cannot decompose this in terms of two closed subsets. So again, you can pick either one of these definitions that you want. They all mean the same thing. And so we're going to use this now to define this quotient here as the coordinate ring of V. Right? So let me maybe give a quick example before we go on. Let's go back to the large case of when X here is the affine n space. Well, this here is an affine variety for the following reason. Remember that we worked out before that the ideal generated by this here should correspond to the zero ideal. This is because every point in AN is a zero of this polynomial. Right, so again, every point here is a zero of this polynomial. And so this here is going to be a prime ideal because my R here is an integral domain. And actually, the coordinate ring is just the polynomial ring. So I can really say now that here, AN of F is an affine variety. Here's an example of a prime ideal. Here's an example of its coordinate ring. All right, so all of this come back to this very general affine n space. So I think I'm not really going to try to do the proof here. Maybe I'll just kind of skim over a couple of ideas so you can see how this goes. So if I assume that those weird statements about V not being decomposed are true, say that I want to prove that IV is a prime ideal. Well, the simple thing is, say that F times G is an IV, then what we can do is we can factor things in this way here. So let's take our set T, which corresponds to a single polynomial. Then I can factor T as a product of 2 by literally just factoring that polynomial as a product of 2 polynomials. And then if you go back to some of the properties that we proved coming down to the Zariski topology, Z of the product is the union of these two Z's. Right, again, this is something that we proved when we worked out the Zariski topology. And so what this literally now means is that V is the union of two things here. And if you just play around with things just a little bit, then you get that, you know, something about how V has to be contained in one of these two, but being contained in one of these two means that F has to be 0 for all P and V. And of course, that just means that F has to be in the ideal. So in other words, if I assume that the product was in this ideal, then I have to conclude that at least one of the factors has to be in the ideal. So I'm not going to worry about the proof here for the sake of time. It's not a very complicated proof. The other direction is also very similar, that if you wanted to, say, assume that IV is prime, then you want to prove that you cannot write this as a composition in this way. So roughly speaking, what you would say is, you know that if V is a union in this way, then IV here has to be this intersection. And if IV is the intersection and IV is a prime ideal, then you actually find that one of these two has to happen. Right? That IV has to equal IV1 or has to equal IV2. And if that's the case, you actually see that V1 has to equal V, right? Because we're dealing with Zariski closed sets. So again, I'm not really going to worry about this for the sake of time. I'll just say that if you wanted to kind of read through the lecture notes, then you can. But hopefully things here will make sense. So next time, what I want to do is come back and play around with this idea again, that we're kind of balancing off of properties of the varieties with properties of IV, that being a prime ideal. And we want to try to use that to understand a little bit more, how do we write down what an abstract affine variety will be. All right, so any questions here before we call it a day? Okay. All right, well, you both take care and see you on Wednesday then. So I hope you have a good rest of the day.
Take care. See you.
Okay.
See you.